Okay, once again, welcome you all back in this third talk on metric spaces. And you know that we have discussed in the previous two talks the definition of a metric, the motivation, why we do define the metric, how do we calculate the distance between any 2 point in R2. There are different, so we defined several matrices, at least 3-4 matrices on R2. We defined at least 3 matrices on R. So it means that it shows that we can always define more than one metric on a non-empty set X. At least one metric which I mentioned that that is the discrete metric we can define, and we can define on R or R2 or Rn the usual matrices. Now, instead of R2, let us take a journal, the set X is equal to Rn, the set of ordered n tuples of real numbers. So, we take the set of all ordered n tuples real numbers. So, let us take here is X is equal to, we have X is equal to X and Y are any 2 points in F's. The coordinates of X are x1, x2, xn, and the coordinates of Y are y1, y2, yn in X. Then, now we defined different kind of matrices. So, first we call this D1 matrix. D1 we define we define D1 is function. So, D1 function on X cross X defined in this way, that D1 xy is equal to summation I runs from 1 to n mod of x1 minus y1. It is same as that it is equal to mod of x1 minus y1 plus mod of x2 minus y2 and plus and so on, plus mod of xn minus yn. So, we are extending the second example. Okay. So, this is and then we define D2 matrix, D2 function dxy is equal to summation I runs from 1 to n, or you instead of mod, or you can write xi minus yi square or whole raised to the power half. It is same as the usual metric. Okay. Then we define dpxy. Okay, dpxy I runs from 1 to n mod of xi minus yi raised to the power p whole raised to the power 1 over p, where p is greater than or equal to 1. Okay, and then we define d infinity, or it is also called max matrix or sup matrix. dxy is equal to maximum of xi minus yi I runs from 1 to n. Okay, so we can see that these 4 are the matrices on Rn. Now, you see that this one is called max matrix, or sometimes we can call it a sub matrix. Okay, this matrix is here. You take the matrix B. It is called the usual matrix, because this is when we calculate the distance between any 2 point in Rn, we calculate by using this formula. Okay, so that's why it is called the usual matrix. And this matrix, the first, it is called taxi cab matrix. Okay, and this is the matrix. So all these are the matrices, and it can be easily, as we have seen in the previous cases, these can be easily seen that these 4 are the matrices on Rn. So to verify that A, B, C, D are the matrices on Rn, it is I think you can do it very easily. You can verify all the properties very easily, except for this metric, for this TP matrix, you need the Minkowskian inequality. Okay, the Minkowskian inequality is given in the appendix. Okay, so but we will use this Minkowskian inequality. So now, so this if suppose you have x, y, z are any 3 elements in Rn whose coordinates are x1, x2, xn, and the coordinates of y are y1, y2, yn, and the coordinates of z are z1, z2, zn. Then to verify the third inequality, fourth property M4 or triangle inequality, we take dpxy is equal to this thing by the definition of this dp. Okay, so this we can write it. Now you can add and subtract zi here is, and then we can write, because we can use the formula, we can use the property of mod, that mod of x plus y is less than or equal to mod of x plus mod of y. So by using this we can write this is mod of xi minus zi plus zi minus yi. Okay, and then here we use the Minkowskian inequality. So by using the Minkowskian inequality, this is less than or equal to the summation of this plus the summation of this, but this is equal to dpxz and this is equal to dpzy, and therefore you can see that dpxy is less than or equal to dpxz plus dpzy. It means that the triangle inequality holds good. So this way we can see that again here we can see that we have defined 4 different kind of matrices on Rn. Of course, beside this you always have a discrete metric on every non-empty set X, and that is, so it is on Rn. Now in the same way as we have defined on Rn, if we consider X is equal to Cn, Cn is the set of ordered n tuples of complex numbers, and then in the same way as in this example we can define the matrices for matrices on X is equal to Cn. Now let us move to different kind of sets. As I mentioned in the very beginning, how do we calculate the distance between any two element in the set of sequences, or in the set of functions, or in the set of bounded sequences, or in the set of convergent sequences? Okay, so we are moving towards the set of all bounded sequences of real or complex numbers. So let us denote L infinity. Okay, so we denote L infinity by the space of all bounded sequences of real or complex numbers. That is to say, L infinity is equal to the set of sequences of real or complex number. Okay, keep in mind either all the sequences of real numbers or all the sequences of complex numbers. So this is the sequence of real numbers such that the sequence is bounded. Sequence is bounded means the supremum of mod of xn is less than infinity. That is to say, the supremum must exist, so there must exist some constant m such that the supremum of xn is less than or equal to that constant. So this is we denote L infinity by the set of all bounded sequences of real or complex number. Keep in mind we will use this all the time. And let us take x and y are two elements of L infinity, but you keep in mind L infinity is what? L infinity is the set of all sequences. So x and y are what? X and y are sequences. So we write x is equal to xn and y is equal to yn. So these are sequences, and then we define a function which we call d infinity from x cross x, from L infinity cross L infinity to R, in this way that the supremum of mod of xn minus yn and supremum is taken over 1 is less than or equal to n is strictly less than infinity. Okay, so we are taking this, you take, and then because this mod of x minus y, okay, satisfy all the properties of a metric, and therefore d infinity, this d infinity is a metric. It can be easily proved that d infinity is a metric on L infinity. D infinity is a metric on N infinity. So this is a metric on N infinity, and L infinity with this metric okay, is a metric space. So this is a metric space. Okay, this you can prove. Now, suppose we have here we are considering the sequence L infinity is the sequence of all space of all bonded sequences. Okay, and then we define this way. Now, suppose if we are removing the word bonded, suppose we are considering the space or the set of all sequences of real or complex numbers. Okay, would this be a metric or not? For example, in the next you see that suppose small s denotes the set of all sequences of real or complex numbers. That is, s is equal to xn, which is real or complex numbers. Okay, these elements, these sequences may not be bounded. Whether this metric on this set, whether this function d infinity on this set S is a metric or not. If it is not, then how we can define? Actually, it would not be a metric. Why it would not be a metric? Because if these sequences are not bounded, then the supremum of this term may tends to infinity. So the distance between x and y is infinity. But what we have considered? The dxy must be a finite number. It should not be infinity. So it is not well defined. Okay, so d infinity xy is not well defined if x and y are any sequences, and therefore d infinity, okay, over this set S of all sequences of real or complex number is not a metric. But we can define another function which we write that dxy is equal to summation I runs from 1 to infinity 1 over 2 raised to the power n mod of xn minus yn divided by 1 plus mod of xn minus yn, where x and y are sequences. X is equal to xn and y is equal to yn of real or complex number. Now look here, sir. Why did we consider this element, this term over here? Without this term, can we say that D is a metric? No, because without this term, the summation may diverge. So this series may diverge. So if this series will diverge, it means that the distance between any 2 points x and y is not well defined, because the distance between any 2 points must be unique, and the sequence is this series is a divergent series, so this point will not be a unique point. So this is very necessary. So now let us see the verification of this, whether this D defined by this is a metric on the set of all real or complex numbers. So we can define this in the following way. Let us verify. So first you see that in the series this series is convergent because the whole term, the nth term is less than 1 over 2 raised to the power n. So this series is convergent. If this series is divergent, then dxy is not well defined. So that's why we are considering this term over here. And from here you can see that this is greater than or equal to 0, is satisfy x is equal to y if and only if dxy is equal to 0, d symmetry property automatically holds, but only the third property, the fourth property, the M4. So for M4, so we need to check. So let us take x is equal to xn, y is equal to yn, and z is equal to zn. We any three sequences in the set S. Then by the triangular inequality, we have this one, xn minus yn is less than or equal to xn minus zn plus zn minus yn. Now, then from here we can see that, keep in mind, now we will use this one. Suppose alpha is less than or equal to beta, then we can add both the side alpha and beta. So here we have alpha beta and here we have alpha beta, and then divide the whole term by 1 plus alpha into 1 plus beta. We will get alpha upon 1 plus alpha is less than or equal to beta upon 1 plus beta. So if alpha is less than beta, then alpha upon 1 plus alpha is less than or equal to beta upon 1 plus beta. So here is, we can see that if you treat this as your alpha, okay, and this term as your beta, then you can see that this upon 1 plus alpha, 1 plus this is less than or equal to this upon 1 plus this. So this upon this one. So this we can write in this way, and then this is same as, so you can open here is, this is plus, you can write plus here, and then we can, and then because this is mod of xn minus zn upon 1 plus this, so this is, we can remove this term, okay, then this is less than or equal to this plus 1 over this term. Similarly, this term is less than or equal to with this one. So the whole term is less than or equal to this. Then we can define, then we can multiply both the side by 1 upon 2 raised to the power n and take the summation I runs from 1 to infinity. We will have this one. And this is what? This is equal to dxy, this is equal to dxz, and this is equal to dzy. So we have seen that dxy is less than or equal to dxz plus dzy. So this way we can prove that the metric defined this way, the function dxy defined in this way is nothing but it is a metric on the space of all sequences of real or complex numbers. Let us take another kind of sequence space, okay, take another kind of sequence space. What is that? Let us take p is greater than or equal to 1 and must be finite, and then we define L infinity. So you keep in mind, we are taking two things, LP and L infinity. Here is P is not equal to infinity. When P is equal to infinity, it is the sequence of all it is the space of all bounded sequences of real or complex numbers. But here without infinity, when P is finite, must be greater than or equal to 1, LP space, it is known as LP space. Keep in mind, it is known as LP space. So LP space is the space of all sequences of real or complex numbers such that this is holds good, okay, such that the n runs from 1 to infinity mod of xn raised to the power p is finite, okay. And now we can define, then how we can find the distance between any 2 points in this space or in this set. So for this, again we have to define a metric, or we have to define a function d, which is a metric. We define a function d on this space, and which should be a metric and should satisfy all the properties of a metric. Let us take here is how we can do it. We can do it in the following way, that we define the dxy is equal to summation I runs from 1 to infinity mod of xn minus yn raised to the power p whole raised to the power 1 over p. Okay. Now again keep in mind, x and y are the sequences. X is equal to xn, y is equal to yn. and then we have this. So then we will see that this D is nothing but it is a metric on LP space, and then LP space with D is a metric space, and by using this formula we can calculate the distance between any two element of LP space. Okay, so to verify that this D, okay, which is defined in this way, is a metric on LP space. So we can easily see that the condition M1, M2, M3 are satisfied. So we can easily verify that the condition M1, M2 are satisfied. To check the third one, again we need to use the Minkowskian inequality. Actually, the proof is almost same as we have done for the case of Rn with the metric dp. Okay, so dp is the same, but only the thing is that in Rn it was x is equal to the set of components. So okay, here is it is x is equal to the sequence. So here sequence x1, x2, xn and so on. So by definition dxy is equal to this one. Okay, so you can add and subtract zn here and zn here, and then you use the mod of x plus y is less than or equal to mod of x plus mod of y. So we and use the Minkowskian inequality, then you can write in this one. Again, the Minkowskian inequality for infinite sum is given in the appendix. So this is less than or equal to this one. And again, this is what? This is your dxz and this is your dzy, and therefore dxy is less than or equal to dxz plus dzy, and therefore this dxy, which is defined in this way, is a metric on LP space. Okay, and therefore LP space with this metric is a metric space. Okay, so this way we can find, we have defined a formula by which we can calculate the distance between any two sequences, okay, of real or complex numbers in the LP space. Now, as I mentioned in the beginning, how we can define the distance between any two functions? If you have two functions, you have a set of functions. So suppose let us consider a set of all bounded real valued functions. Set of all bounded real valued functions defined on the closed interval AB. For example, let me write BAB. We denote BAB by the set of all bounded real valued functions defined on the closed interval AB. That is to say, BAB is the set of all functions f defined on the closed interval AB to R, set of all real valued functions from the closed interval AB to R, such that the f of t is less than or equal to k for all t in this one and for some constant k. That is to say, this f is a bounded function. Okay, so this is less than or equal to k. Then we define a function d f g on BAB in this way, that supremum of f of t minus gt and supremum is taken over t in the closed interval AB. And then again, by using the property of mod, we can see that this function d satisfies all the properties of a metric, and therefore d is a metric on BAB, okay, and BAB with this metric d is a metric space. And in this way, we can, by using this formula, we can define we can calculate the distance between any two elements in a set of all bounded real valued functions defined on the closed interval AB. So that is the way to define this one. Okay. So now I stop over here, and we will see some more examples in my next talk. So thank you very much.